Hello girls, we're going to have a look at something called experimental probability today. And our goal is to answer the following question. What do we do if we can't work out the probability of an event by listing the sample space? So up until this point, we've calculated probability by looking at the size of a sample space, counting the number of things in the sample space, and then counting the number of things that we're interested in and dividing them by each other. But sometimes it's not possible to count the entire sample space, or sometimes it's not appropriate. So let's think about some examples. Say we wanted to know the probability that a horse would win a race. We could look at all the horses and we could say, well, here's the one horse that I'm interested in winning the race, but the individual probabilities of different horses winning is not equal. So we need to come up with a way of defining probability that's perhaps a little bit more sophisticated. What we do in examples like this, and other examples which we'll get to later, what we do is we use something called experimental probability. So experimental probability is called experimental probability because we conduct a large number of trials or experiments to work out the probability of a particular event. So we see how often the result that we're interested in turns up in all the large number of trials, and that gives us a probability calculation. The more trials we do, obviously, the more accurate our probability calculation is going to be. So here, this formula here is the basic formula for experimental probability. The number of trials is now the denominator of that fraction, and the number of times the outcome that we're interested in happens during those trials is the numerator. So in the long run, the more trials that we do, the closer the experimental probability gets to the real probability of the event. The other thing about experimental probability is it allows us to calculate something called the expected number of occurrences, which is the probability that we've got from our large number of trials times the number of times that we conduct the experiment. So I'm going to do an example which hopefully will make some of this a bit more concrete. We're going to have a look at a box which contains an unknown number of coloured balls, and a ball is drawn from the box and then replaced. So first of all, we recognise that because we don't know the number of coloured balls, we don't know which ones are which colours, etc., we don't know how many's in the box, it's not possible for us to calculate the probability of any event in the way that we've been used to doing it. We can't say, okay, there's this number of balls and there's this many of them that are red or blue or whatever, and calculate the probability that way. So what they're going to do in this example is use experimental probability to find the probability of a red ball. And they do that by conducting a lot of trials, a trial being drawing a ball from the box and then putting it back in. They do that 100 times, and they record the colour of the ball that's drawn each time. And they noted in particular that 25 red balls were recorded. So very simply, to find the experimental probability for the number of red balls, all I have to do is so here's how we find the probability, the experimental probability of choosing a red ball, we look at the number of red balls that turned up in the trials divided by the number of trials. So, of course, we can see that the number of red balls is equal to 25, and we divide that by the number of trials, which is 100. Or, in other words, the probability of a red ball is 0.25 or 25%. Okay, that's a pretty straightforward example. Let's have a look at the second section of this example. Find the expected number of red balls if the box contained 500 balls in total. So the question's slightly different now. What they're asking us to do is to apply the probability that we found, is 0.25, to a new number of balls. That's the 500 balls. So in other words, what we're doing is the expected number of red balls. So that's going to be equal to the probability times the number of balls. So the expected number of red balls is equal to the probability of choosing a red ball, which we worked out up here, times the number of balls. So, and the number of balls in this particular question is now 500. So that'll be equal to 0.25 times 500, which is of course equal to 125 red balls. So in a bag of 500 balls we would expect 125 of them to be red. Okay, what I'd like you to do now is in exercise 9F, have a go at all the even numbered questions. And I'll talk to you later. Bye.